Imagine looking up at the winter sky and watching a star explode in real time, not through a telescope, not in some distant galaxy. Right there, in Orion's shoulder, bright enough to read a book at midnight. That's not science fiction, that's Betelgeuse, and it's overdue for the most spectacular death in recorded human history. But here's where it gets weird. In 2026, scientists confirmed something they weren't expecting to find. A hidden companion star called Siwarha, quietly orbiting through Betelgeuse's outer layers, stirring up chaos, accelerating its death in ways that break every model we have. The star is rotating too fast, it's shedding mass too quickly, and nobody can agree on whether it'll explode tomorrow or in 10,000 years. Stick around until the end, because the latest evidence suggests we might be watching the final act of a stellar murder, and Earth has front row seats. Subscribe and follow along, because when Betelgeuse's light finally arrives, what we observe will reveal whether we truly understood stellar death or missed something fundamental about how the universe touches worlds like ours, a cosmic influence that's been quietly shaping our skies all along. There is a star in the night sky that shouldn't be doing what it's doing. You've probably seen it if you've ever looked up at Orion on a winter night. That red-orange shoulder glowing in the constellation of the Hunter. Its name is Betelgeuse, and for most of human history, it has been one of the most reliable landmarks in our celestial navigation. But in 2026, everything we thought we understood about this star came crashing down. Not because it exploded, because something else did something far more unsettling. It revealed that Betelgeuse has been lying to us about what it really is. Let me be clear about something from the start. This isn't a story about a star acting a little strange. This is about a star that is currently violating multiple assumptions about how massive stars are supposed to die, and doing so in ways that force us to reconsider whether we've been watching the wrong clock this entire time. The 2026 confirmation wasn't just another astronomical footnote. It was the moment when scientists confirmed the existence of Siwarha, a hidden companion star that has been orbiting Betelgeuse in silence, disturbing its outer layers, and potentially accelerating its demise in ways we're only beginning to understand. Siwarha isn't massive in the traditional sense. It's not a heavyweight companion that you'd expect to show up in every observation. What makes it dangerous is the wake it leaves behind as it plows through Betelgeuse's extended atmosphere. Imagine dragging a boat through thick molasses at high speed. The molasses doesn't just part, it churns, it heats up, it gets thrown outward in unpredictable directions. That's what's happening here. Except instead of molasses, we're talking about superheated plasma ejected from a star that's already on the edge of stability. The companion's orbital motion is stirring Betelgeuse's envelope like a spoon in boiling soup, and that stirring is doing something we didn't account for in any of our models. The rotation rate is the first red flag. Betelgeuse is spinning at approximately 15 kilometers per second at its equator. That might not sound fast until you realize that a red supergiant of its size and evolutionary stage should be rotating at maybe 1 or 2 kilometers per second, tops. Stars like Betelgeuse expand so dramatically in their final phases that angular momentum gets spread out over an enormous volume, slowing them down to a crawl. It's basic physics, conservation of angular momentum in action. Except Betelgeuse didn't get the memo. Something has been pumping energy back into its rotation, and the only plausible culprit is gravitational interaction with a companion that has been transferring momentum over thousands of years. This isn't just an interesting quirk. Rotation changes everything about how a star dies. It affects the geometry of core collapse, the direction of mass ejection, and most critically, the symmetry of the supernova explosion itself. If Betelgeuse is spinning faster than it should be, then every timeline estimate we've constructed based on internal stellar evolution is now suspect. We've been using a clock that assumes the star has been evolving in isolation, peacefully converting hydrogen to helium to carbon to oxygen in its core like a well-behaved stellar citizen. But if an external force has been meddling with its angular momentum budget for millennia, then we don't know what time it is anymore. The mass loss rate is the second anomaly, and it's even more disturbing. Betelgeuse is shedding material at a rate that shouldn't be sustainable. Recent observations suggest it's losing the equivalent of Earth's mass every 10,000 years or so, which sounds slow until you realize that's orders of magnitude higher than theoretical predictions for a star at its stage. And here's where it gets worse. The mass isn't being lost uniformly. It's directional. There are asymmetries in the outflow that suggest something is pushing material preferentially in certain directions, almost like the star has developed weather systems on a scale so incomprehensibly large that they're carving chunks out of its own surface. The great dimming of 2019 and 2020 should have been our first warning. We thought we understood it. We explained it away as a dust cloud, a temporary obscuration caused by a particularly vigorous convection cell ejecting material that cooled and condensed into sooty particles, blocking our view like cosmic smog. And to be fair, that explanation worked for the dimming itself. But it didn't explain the violence. It didn't explain why the convection cell was the size of multiple astronomical units, larger than the orbit of Mars. It didn't explain why Betelgeuse's surface was behaving like a pot of water just before it boils over, with massive plumes of superheated gas erupting and collapsing in chaotic cycles. What we now suspect is that the Great Dimming wasn't an event. It was a symptom. It was the first time Betelgeuse's instability became visible to us in a way we couldn't ignore, but the underlying problem has been building for much longer. The star's envelope is no longer in equilibrium. Something has destabilized the balance between radiation pressure pushing outward and gravity pulling inward, and that something appears to be mechanical, stirring from a companion we only just confirmed exists 2 years ago. The timing is almost offensive in its implications. We've been watching this star for decades, modeling it, predicting it, and all along there was a massive variable hiding just outside our observational resolution. Here's the uncomfortable question nobody wants to ask out loud, but everyone is thinking. If the companion star has been injecting angular momentum and stirring up asymmetric mass loss, how much of Betelgeuse's current state is due to natural evolution, and how much is induced chaos? Are we watching a star that's dying on schedule? Or are we watching a star that's being killed prematurely by tidal harassment? And if it's the latter, then every estimate of its remaining lifetime, 10,000 years, 100,000 years, tomorrow, is built on a foundation that just crumbled beneath our feet. Let's go back to late 2019, when Betelgeuse started doing something it had never done in recorded history. It dimmed. Not by a little, by a lot. At its faintest, it dropped to less than 40% of its usual brightness, making it the dimmest it had been since we started keeping systematic records. For astronomers who monitor variable stars, this should have been exciting, but not terrifying. Betelgeuse is a semi-regular variable. It brightens and dims on roughly predictable cycles as its outer layers expand and contract. But this wasn't part of the pattern. This was something else entirely. The first reaction from the scientific community was measured optimism. Maybe, just maybe, this was it. Maybe Betelgeuse was finally going supernova, and we were about to witness the astronomical event of the millennium from a front row seat 650 light years away. Social media erupted with speculation. News outlets started running stories about the imminent explosion. There was genuine excitement mixed with a touch of existential dread, because even though 650 light years is far enough to be safe, the idea of watching a star die in real time carries a certain psychological weight. We were ready for the fireworks, except the fireworks didn't come. Betelgeuse started brightening again in early 2020, and by mid-year it had returned to something resembling normal behavior. The disappointment was palpable. but scientists are nothing if not persistent. They turned their attention to figuring out what had actually happened, and what they found was both reassuring and deeply unsettling at the same time. The dimming was caused by a massive ejection of material from the star's southern hemisphere, which cooled rapidly into a cloud of dust particles that blocked a significant fraction of Betelgeuse's light from reaching Earth. Simple, elegant, case closed. Except it wasn't simple, and it definitely wasn't closed. The amount of material ejected was staggering. We're talking about a mass comparable to several times the mass of Earth's moon, hurled into space in what appeared to be a single convulsive event. For context, that's not normal stellar mass loss. That's a cataclysm. And the convection cell that drove the ejection was enormous. Estimates put it at over 1 astronomical unit across, which means it was larger than the distance between Earth and the Sun. Betelgeuse's surface isn't gently bubbling like a pot of simmering soup. It's violently churning like a witch's cauldron in a hurricane. The dust cloud explanation worked for the dimming, but it raised more questions than it answered. Why that particular convection cell? Why that amount of mass? Why then? Stars don't just randomly decide to cough up moon-sized chunks of themselves without a reason. There has to be an underlying driver, some mechanism that's pushing Betelgeuse's surface dynamics into overdrive. And this is where the 2026 discovery of Siwarha starts to matter in a big way. If a companion star has been gravitationally stirring Betelgeuse's outer envelope for thousands of years, then what we saw in 2019 wasn't a random fluke. It was a predictable consequence of a system under stress finally reaching a breaking point. Recent reanalysis of the dimming event has revealed something even more concerning. The mass ejection wasn't symmetric. It came primarily from one hemisphere, creating an asymmetric distribution of material around the star. This matters because symmetry is everything in stellar physics. When a star explodes as a supernova, we generally assume the explosion propagates outward in all directions more or less equally. That assumption breaks down if the star has already been shedding mass preferentially in one direction before the core collapses. Suddenly, you're not looking at a spherical explosion anymore. You're looking at a shaped charge, and shaped charges have directionality. The implications cascade from there. If Betelgeuse is losing mass asymmetrically, then its envelope is no longer uniform. There are regions that are denser, regions that are more tenuous, regions where the pressure gradient is steeper. When the core finally collapses and the shockwave races outward through the envelope, it's going to encounter varying resistance depending on which direction it's traveling. That means the supernova won't be a clean, symmetric burst of light and energy. It'll be lopsided, with some directions receiving more energy than others. And if we happen to be in one of those preferred directions, the observational consequences could be significantly different from what we're expecting. This is where plasma convection enters the picture, and where things get truly alien. Betelgeuse's outer layers aren't static. They're constantly rising and falling in enormous convection cells, driven by the difference in temperature between the hot interior and the cooler surface. We see this on the Sun too, but on the Sun, the convection cells are maybe 1,000 kilometers across. On Betelgeuse, they're larger than the orbit of Mars. These aren't gentle flows. They're titanic rivers of plasma moving at speeds of tens of kilometers per second, carrying thermal energy and mass in chaotic patterns that we're only beginning to map. The size of these convection cells matters for a reason that doesn't immediately seem obvious. When you have fluid motion on such an enormous scale, the timescales involved become very long. A single convection cell might take months or years to complete one cycle of rising and falling. That means the surface of Betelgeuse isn't responding to changes in the core in real time. There's a lag. There's inertia. If something changes deep inside the star, it could take years for that change to manifest as visible behavior on the surface. Which means when we look at Betelgeuse and see it dimming or brightening, we're not seeing what's happening now. We're seeing what happened years ago, filtered through billions of tons of roiling plasma. The more we study the Great Dimming, the more it looks like a warning shot. It was Betelgeuse showing us that its surface dynamics are no longer stable, that the balance between internal pressure and gravitational collapse is shifting in ways we didn't anticipate. And if the companion star is the culprit, if Siwarha has been mechanically disturbing Betelgeuse's envelope and amplifying instabilities that would have otherwise remained manageable, then the dimming wasn't an isolated event. It was the first visible crack in a structure that's been weakening for a very long time. And once mass loss becomes directional, once the symmetry breaks, the physics of core collapse change in ways that make every prediction we've ever made suddenly unreliable. There's a rule in astrophysics that's so fundamental, so deeply embedded in our understanding of stellar evolution, that when a star breaks it, we have to stop and reconsider everything. The rule is this: as a star expands into a red giant or supergiant, its rotation slows down. It's not optional. It's not negotiable. It's a direct consequence of conservation of angular momentum, one of the few truly sacred principles in physics. When a figure skater pulls their arms in, they spin faster. When they extend their arms, they spin slower. A star expanding to a size large enough to swallow the inner solar system should be spinning so slowly that its rotation becomes almost negligible. Betelgeuse is spinning at 15 kilometers per second. That's not slow. That's impossible. Let me put that number in perspective for you. Betelgeuse has a radius roughly 1,000 times larger than the Sun. If it were rotating at the rate we'd expect from simple conservation of angular momentum, based on what it must have been doing when it was a smaller main sequence star, it should be rotating at maybe 1 or 2 kilometers per second at most. Instead, it's rotating at 15. That's a discrepancy of nearly an order of magnitude. And in astrophysics, when your observations differ from your predictions by that much, it's not a rounding error. It's a sign that something fundamental is happening that you didn't include in your model. The traditional explanation for anomalous rotation in evolved stars is stellar cannibalism. Maybe Betelgeuse wasn't always alone. Maybe it once had a binary companion that spiraled inward over millions of years, eventually being consumed and shredded by Betelgeuse's expanding envelope. When you eat another star, you also absorb its angular momentum, and if that star was in a close orbit moving fast, the momentum transfer could be significant. It's a violent, chaotic process, but it would leave behind exactly what we see: a rapidly rotating red supergiant with no visible companion. Case closed, right? Not anymore. The 2026 confirmation of Siwarha throws a wrench into that neat explanation because Siwarha is still there. It hasn't been consumed. It's orbiting at a comfortable distance, stirring up Betelgeuse's atmosphere, but not merging with it. So either Betelgeuse ate one companion and still has another one left over, which would make it an extraordinarily messy system, or the rotation we're seeing isn't from a past merger at all. It's from ongoing gravitational interaction with Siwarha, which has been transferring angular momentum through tidal forces over thousands or tens of thousands of years. And that possibility is much, much worse for our timeline estimates. Here's why it matters. If Betelgeuse absorbed a companion star millions of years ago, then the rotation we see today is a leftover artifact of that ancient event. It's not actively changing. It's not getting worse. The star has had plenty of time to adjust to its new angular momentum budget and continue evolving toward core collapse at a predictable rate. But if Siwarha is actively transferring momentum right now, then Betelgeuse's rotation is still increasing. The system is still evolving dynamically, and we have no idea when or if it will reach equilibrium before the core runs out of fuel and collapses. We're not watching a static object anymore. We're watching a system in flux, and flux means unpredictability. Rotation does terrible things to the geometry of core collapse. When a massive star's core runs out of nuclear fuel, It collapses catastrophically under its own gravity in a matter of seconds, rebounding into a supernova explosion. We've modeled this process extensively, and in non-rotating stars, the collapse is more or less spherically symmetric. The shockwave propagates outward in all directions equally. The star explodes uniformly, and we get a nice, predictable light curve. But add rotation, and everything changes. Centrifugal forces become significant. Material at the equator gets flung outward more easily than material at the poles. The core doesn't collapse symmetrically. It forms an oblate shape, a pancake rather than a sphere. And depending on how fast it's spinning, the explosion can become highly directional. This brings us to a question that nobody really wants to think about, but everyone quietly acknowledges in the back of their minds. Are we watching a star that has been re-energized, too late to stabilize? Is Betelgeuse like a boxer who's taken too many hits to the head and is stumbling forward on pure momentum? Not because they're strong, but because they haven't realized they're already beaten. The analogy isn't perfect, but the idea is sound. If gravitational interaction with Siwarha has pumped energy and angular momentum into Betelgeuse during a phase when it should have been winding down, then the star's internal structure might be fighting against itself. The core wants to collapse. The envelope wants to expand. The rotation wants to fling material outward. And all of these competing forces are pulling in different directions, creating instabilities that compound over time. The more rotation you add to a collapsing core, the more likely you are to form structures that don't happen in symmetric explosions. Jets, for instance. High-energy beams of matter and radiation that shoot out along the rotation axis, carrying enormous amounts of energy in a tightly focused cone. We see this in gamma-ray bursts, which are thought to be the most extreme version of core collapse in the universe, where a rapidly rotating stellar core collapses directly into a black hole and launches jets at nearly the speed of light. Betelgeuse isn't going to make a black hole. It's not massive enough, but it is rotating fast enough that jets are no longer a theoretical impossibility. They're a plausible outcome, and that changes the risk profile dramatically. Nobody is saying Betelgeuse is about to turn into a gamma-ray burst. Let's be clear about that. The physics doesn't support it. But what people are starting to quietly discuss in conference rooms and research papers is whether Betelgeuse could produce something intermediate, a jet-driven supernova that's more asymmetric than we've been planning for. And asymmetry means directionality. It means that instead of a uniform shell of energy expanding outward in all directions, we might get a concentrated blast along certain axes with weaker emission in others. And if Earth happens to be positioned along one of those axes, the energetic consequences could be significantly different from our baseline expectations. The rotation problem doesn't have a clean solution. It's not a puzzle we can solve with more observations or better models, because the fundamental issue is that we don't have enough constraints. We don't know exactly when Siwarha started interacting with Betelgeuse. We don't know how much angular momentum has been transferred. We don't know if the transfer is ongoing or if it already peaked centuries ago. And without that information, we can't build a reliable clock. We can't say with confidence whether Betelgeuse will explode in 10,000 years or 10 years, or whether it already has, and the light just hasn't reached us yet. That uncertainty is the most dangerous thing in astrophysics, because it forces us to admit that we might not see it coming until it's already here. There's a type of conversation that happens in astrophysics conferences late at night, after the formal presentations are over, and people are gathered in small groups over drinks, talking about things they wouldn't say on stage. The conversation usually starts with someone asking, half joking, whether we've checked if Earth is in the line of fire. And then someone else points out that we actually haven't, not really, because we don't know where the line of fire is. We don't know Betelgeuse's rotation axis. We don't know if it's tilted toward us or away from us or sideways. And if the star goes supernova and launches jets, which is starting to look like a real possibility, then knowing the axis becomes the single most important piece of information we don't have. Let's talk about why jets form in the first place, because this isn't some exotic phenomenon that only happens in distant galaxies. Jets are a natural consequence of rotation plus asymmetric collapse. When you have a spinning object that's collapsing under gravity, conservation of angular momentum forces material to flatten into a disk around the equator. But along the rotation axis, at the poles, there's less material and less resistance. So if you have a sudden release of energy, like say a core collapse supernova, the path of least resistance is along the poles. Energy and matter get channeled preferentially in those directions, forming narrow, high-velocity outflows that we call jets. It's the same basic mechanism that powers everything from young stellar objects to quasars. The physics scales, and Betelgeuse has all the ingredients. Now, here's where it gets uncomfortable. When we talk about the danger from a supernova, most people think about brightness. They imagine the star exploding and becoming so luminous that it outshines the moon, visible during the daytime, turning night into twilight for weeks. And yes, that will happen. Betelgeuse will absolutely become one of the brightest objects in the sky when it goes supernova, bright enough to cast shadows at night, bright enough to read by. But brightness isn't the danger. Light is just photons, and photons at visual wavelengths don't do much harm at 650 light years. The real danger, the thing that keeps certain scientists up at night, is what happens if those jets are pointed in our direction and they're carrying high-energy radiation that our atmosphere isn't prepared to handle. Gamma rays are the problem, not the kind you get from medical equipment or even from nuclear decay. We're talking about ultra-high-energy gamma rays. Photons with so much energy that when they hit Earth's atmosphere, they create cascades of secondary particles that can strip electrons off molecules, ionize gases, and disrupt chemical bonds on a massive scale. Earth's atmosphere is pretty good at absorbing gamma rays. It's one of the reasons life exists on the surface in the first place. But there are limits. If you dump enough high-energy radiation into the upper atmosphere all at once, you start breaking down ozone molecules faster than they can reform. And ozone is what protects the surface from ultraviolet radiation. Lose the ozone layer, and you've got a problem that lasts for years, potentially decades. The gamma ray burst risk from Betelgeuse has been discussed and largely dismissed by the mainstream scientific community, and for good reason. True gamma ray bursts require either a black hole formation or an extremely massive, rapidly rotating stellar core collapsing into a neutron star under very specific conditions. Betelgeuse doesn't meet those criteria. It's massive, but not massive enough. It's rotating fast, but probably not fast enough. The consensus is that Betelgeuse will produce a Type II supernova, a relatively ordinary core collapse event that will be spectacular, but not existentially dangerous. But consensus is built on models, and models are built on assumptions. And one of the assumptions we've been making is that Betelgeuse has been evolving in isolation without significant external perturbations. That assumption is now in question. What if the jets aren't gamma ray bursts, but something intermediate? What if Betelgeuse produces a mildly collimated explosion, not as extreme as a GRB, but not as symmetric as a standard supernova? There's a growing body of evidence from supernova remnants suggesting that many core collapse events are more asymmetric than we thought. We see elongated structures. We see preferential directions of mass ejection. We see signs that the explosion wasn't a perfect sphere, but more like an ellipsoid, or even a bipolar outflow. If Betelgeuse follows that pattern, and if we happen to be positioned near one of the preferred directions, then the flux of high-energy particles and radiation we receive could be significantly higher than the baseline predictions. The uncertainty around axis orientation is maddening, because it's such a simple question with enormous consequences, and we don't have a good answer. Betelgeuse's surface is so roiling and chaotic that measuring its rotation axis directly is incredibly difficult. We can infer rotation from Doppler shifts in spectral lines, but that tells us the speed, not the direction. We can look for asymmetries in surface features, but those change on timescales of months, making it hard to determine what's a stable axis and what's just turbulent noise. The best estimates we have suggest the rotation axis might be tilted relative to our line of sight, but the error bars are huge. We're essentially saying it could be pointing anywhere from almost directly at us to almost perpendicular, and that range of uncertainty encompasses completely different risk scenarios. Let me be very clear about something, because this is where speculation starts to blur into fear-mongering if we're not careful. Nobody is predicting an extinction event. Nobody is saying Betelgeuse is going to sterilize Earth or wipe out the biosphere or cause mass casualties. The distance is too great. Even if Betelgeuse launched jets directly at us, the energy flux would be manageable. We'd see atmospheric effects, possibly some temporary disruption to satellite systems from increased radiation, maybe a slight uptick in cosmic ray exposure. But this isn't an asteroid impact scenario. It's not civilization ending. What it is, though, is a reminder that the universe can reach across vast distances and touch our planet in ways we're still learning to predict. The atmospheric coupling question is where this gets truly interesting from a scientific standpoint, because it's an area where astrophysics meets geophysics and climate science, and nobody really knows what the long-term effects might be. Ozone depletion isn't a binary on-off switch. It's a gradual process that can persist for years, affecting UV penetration, altering atmospheric chemistry, potentially influencing weather patterns through changes in stratospheric heating. We have some experience with this from human-caused ozone depletion in the late 20th century, but that was a slow, chronic problem. A sudden injection of high-energy radiation from a supernova would be an acute shock, and the recovery dynamics could be very different. We don't have good models for this. We don't have historical analogs. We're extrapolating from limited data, which is always dangerous. And here's the really uncomfortable part. Even if Betelgeuse's rotation axis is pointed away from us, even if the jets go in completely different directions and Earth gets nothing but the symmetric component of the explosion, we still don't fully understand what happens to a planetary magnetosphere when it's suddenly exposed to a sharp increase in cosmic ray flux. Our magnetosphere protects us from solar wind and cosmic radiation by deflecting charged particles around the planet. But it's not a perfect shield. Some particles get through, especially near the poles where the field lines converge. If you suddenly increase the flux by orders of magnitude, even temporarily, you could start seeing effects we've never observed before. Enhanced auroral activity, induced currents in power grids, increased radiation exposure for high-altitude flights and space missions. None of this is catastrophic, but it's all disruptive, and disruption at planetary scales has a way of cascading into unexpected consequences. The question nobody likes discussing isn't whether Betelgeuse will explode. It's whether we're ready for what comes after. And the honest answer is, we don't know, because we've never had a nearby supernova during the era of technological civilization. The last time a supernova went off close enough to Earth to leave a detectable signal in the geological record was maybe a few million years ago, long before humans existed. We're flying blind, making educated guesses based on physics we understand pretty well, and edge cases we don't understand at all. And that's why the directional risk matters, even if the absolute risk is low. Because the difference between low and negligible is the difference between something we can prepare for and something we're just hoping won't happen. If you ask an astrophysicist when Betelgeuse will explode, they'll give you an answer that sounds reassuring at first, and then becomes progressively more unsettling the more you think about it. They'll say something like, probably within the next 100,000 years, which sounds like a comfortably distant time frame, until you realize that within 100,000 years includes tomorrow. It includes next year. It includes the possibility that the star already exploded 650 years ago, and the light is currently racing toward us through interstellar space, scheduled to arrive on a Tuesday afternoon while you're making coffee. The word imminent in cosmology is a trap. It hides uncertainty behind a veneer of precision. The fundamental problem with timing stellar explosions is that everything happens behind closed doors. The final stages of a massive star's life play out deep inside the core, where temperatures reach billions of degrees and densities become comparable to atomic nuclei. We can't see inside. We can't send probes. We have to rely on indirect evidence from surface behavior and theoretical models, and both of those sources have significant error bars. A star can spend millions of years fusing hydrogen into helium, hundreds of thousands of years fusing helium into carbon and oxygen, thousands of years working through heavier elements, and then less than a day fusing silicon into iron before collapsing. That final stage is essentially invisible from the outside until it's already happened. Iron is the end of the line for fusion. Every element lighter than iron releases energy when it fuses into something heavier. That's how stars generate the pressure that holds them up against gravity. But iron is different. Fusing iron into heavier elements doesn't release energy. It consumes energy. So when a star's core finally converts all its silicon into iron, the fusion stops. There's no more outward pressure. There's nothing left to prevent gravity from winning. The core collapses in about 1 second, rebounding into a shockwave that rips through the star and blows it apart. From the outside, the first sign you'd see is a sudden spike in neutrino emission, followed several hours later by the optical brightening as the shockwave reaches the surface. By the time you see the light, the explosion is already over. Here's the terrifying part. We don't know how much iron is in Betelgeuse's core right now. We can't measure it directly. We can estimate based on models of stellar evolution, plugging in Betelgeuse's mass and composition and rotation, and running simulations forward in time to see when iron formation should begin. But those models depend on assumptions about mixing, mass loss rates, internal structure, and a dozen other parameters that have large uncertainties. Different models give you different answers, ranging from iron core formation has already started to it won't begin for another 10,000 years. That's not a typo. Our best models disagree by 4 orders of magnitude about when Betelgeuse will reach the critical threshold. The 2026 discovery of Siwarha makes this uncertainty even worse, because now we have to account for external perturbations that weren't in the original models. If the companion star has been stirring Betelgeuse's envelope and enhancing mass loss, that affects the pressure balance throughout the star. It affects how quickly material gets mixed from the envelope down into the core. It affects the thermal structure, the convection patterns, the rotation profile, all of which feed into the iron formation timeline. And we don't have precise measurements of any of these effects, because we only just confirmed Siwarha exists. We're trying to update models that took decades to develop using data we've had for less than 2 years. The error bars aren't shrinking, they're expanding. There's also the lag illusion to contend with, which is one of those subtle mind benders that astrophysics loves to throw at you. When you look at Betelgeuse, you're seeing light that left the star 650 years ago. That's not a metaphor. That's literally what's happening. The photons hitting your eye right now started their journey before the printing press was invented, before Columbus sailed to the Americas, before the Renaissance began. Which means if Betelgeuse exploded in, say, the year 1400, we wouldn't know yet. The supernova light wouldn't have reached us. As far as we're concerned, the star is still there, still flickering in Orion's shoulder, completely oblivious to the fact that it no longer exists. This creates a deeply weird situation where we're observing a star that might already be gone, and there's absolutely no way to know until the light arrives. You can't send a signal faster than light. You can't cheat relativity. You can't call ahead and ask Betelgeuse if it's still there. You just have to wait, watching a ghost image of a star that may or may not be real anymore, and hope that if it has exploded, we'll get some warning before the full intensity of the blast hits our atmosphere. And that's where neutrino astronomy comes in, which is both hopeful and frustrating in equal measure. Neutrinos are the closest thing we have to an early warning system for supernovae. They're produced in staggering numbers during core collapse, and unlike photons, they don't interact much with matter. They just fly straight through the star without scattering or being absorbed, escaping hours or even days before the optical light does. If Betelgeuse collapses, neutrino detectors on Earth should see a spike in neutrino flux roughly 3 to 4 hours before we see the visible brightening. That's our warning window. 3 to 4 hours to alert observatories, reorient telescopes, notify the public, and prepare for what's about to become the most observed astronomical event in human history. Except there's a catch, because of course there is. Neutrino detectors are incredibly sensitive instruments designed to catch the tiniest interactions between neutrinos and matter, but they're not omniscient. The detection depends on distance, neutrino energy, and detector sensitivity. For a supernova at 650 light-years, we'd expect to see maybe a few dozen neutrino events in the largest detectors, which is enough to confirm something is happening, but not enough to give us detailed information about the collapse geometry or energy distribution. And if we're unlucky, if the detectors happen to be offline for maintenance or calibration when the neutrinos arrive, we might miss the warning entirely. We'd go from business as usual to supernova in the sky with no transition, no preparation, just sudden cosmic violence appearing overhead. The companion star complicates the timing estimates in ways that are hard to quantify. If Siwarha is orbiting through Betelgeuse's envelope, it's depositing energy and angular momentum in a time-varying way that depends on orbital position. Sometimes it's closer to the star, stirring more vigorously. Sometimes it's farther away, and the stirring decreases. This creates a periodic modulation in Betelgeuse's internal structure that our models aren't sophisticated enough to handle yet. We can simulate isolated stars just fine. We can even simulate binary systems where both stars are compact and well-defined. But a giant star with a smaller companion plowing through its atmosphere is a messy, three-dimensional, time-dependent problem that requires enormous computational resources to solve properly. At this point, the question stops being when and becomes what else behaves like this. If Betelgeuse is experiencing late-stage instabilities driven by binary interaction, is it unique? Or is this a common phenomenon that we've been missing because we don't have enough resolution to detect companions around other red supergiants? How many other massive stars in our galaxy are quietly harboring hidden partners that are stirring up their envelopes and accelerating their deaths? And if this is common, then our entire framework for understanding supernova rates, progenitor statistics, and explosion mechanisms might need revision. Betelgeuse isn't just a ticking clock anymore. It's a test case for whether we understand how massive stars die at all. Betelgeuse might be the star everyone knows, the one that makes headlines every time it does something weird, but it's not the only red supergiant misbehaving right now. Over the past 2 years, observations from multiple telescopes and surveys have revealed a pattern that's starting to make astronomers nervous. There are other massive stars showing similar instabilities, unexplained dimming events, anomalous rotation rates, asymmetric mass loss. And the more we look, the more we find. It's starting to look less like Betelgeuse is a unique cosmic oddball, and more like it's just the closest, brightest example of something that might be happening all over the galaxy. Take VY Canis Majoris, for instance. For it's one of the largest known stars, a red hypergiant so enormous that if you placed it where the sun is, its surface would extend past the orbit of Jupiter. It's also losing mass at a truly staggering rate, ejecting material so fast that it's surrounded by a complex nebula of dust and gas that looks like an explosion in slow motion. Recent observations from 2025 showed unexpected asymmetries in that nebula, suggesting the mass loss isn't uniform. Something is pushing material preferentially in certain directions, and the most likely explanation is either rotation or a companion star or both. Sound familiar? Then there's Antares, another red supergiant in Scorpius, which has been showing unusual variability patterns over the past few years. Its brightness fluctuates on timescales ranging from weeks to years, and the amplitude of those fluctuations has been increasing. In 2026, high-resolution imaging revealed that Antares has a companion star, which wasn't exactly news. We've known about Antares B for over a century. But what was news is that the companion appears to be interacting with Antares' extended atmosphere in ways we didn't predict. There's evidence of a bow shock, a wake structure similar to what we see with Betelgeuse and Siwarha. 2 data points don't make a trend, but 3 starts to look like a pattern. The pattern extends beyond individual stars to the broader population of red supergiants as a whole. Surveys using automated telescopes and machine learning algorithms to monitor thousands of stars simultaneously have detected an unexpectedly high number of dimming events, similar to Betelgeuse's Great Dimming. Not identical, each star is unique, with its own mass, composition, rotation, and evolutionary history, but statistically significant. We're seeing more massive stars undergoing sudden, dramatic brightness drops than our models predict, and in many cases, those dimming events are accompanied by spectroscopic evidence of mass ejection and surface instability. This is where the story gets uncomfortable for a specific reason. If late-stage massive stars are inherently more unstable than we thought, then our entire framework for predicting supernova rates is built on shaky ground. We've been assuming that red supergiants spend a relatively stable period in that phase, slowly fusing heavier elements in their cores while maintaining a more or less steady envelope. But if they're actually experiencing violent chaotic mass loss driven by rotation, convection, or binary interaction, then the timescale between entering the red supergiant phase and exploding could be much shorter than we've been estimating. And shorter timescales mean higher supernova rates, which has implications for everything from galactic chemical evolution to cosmic ray production. The emerging evidence suggests that late-stage stellar evolution is messier than our models assume. Models are necessarily simplified. You can't simulate every convection cell, every density fluctuation, every magnetic field twist. You have to make approximations, and those approximations generally assume that stars are roughly spherical, roughly symmetric, and evolving in isolation. Real stars don't always cooperate. Real stars have companions. They rotate, they develop large-scale instabilities, and they interact with their environments in ways that create feedback loops we're still learning to understand. The more detailed observations we get, the more we realize that the simple picture we've been using is missing critical physics. One of the most intriguing developments from late 2025 is the application of machine learning to stellar modeling. Researchers have been training neural networks on massive datasets of stellar observations, teaching the algorithms to recognize patterns and correlations that human astronomers might miss. And those algorithms are finding anomalies. They're flagging stars that don't fit the standard evolutionary tracks. Stars whose properties suggest they're evolving faster, or slower, or in different directions than theory predicts. Some of those stars are red supergiants. Some of them are showing signs of binary interaction, or enhanced mass loss, or rapid rotation. And a non-trivial fraction of them are within a few thousand light years of Earth, close enough that when they explode, we'll see it. What's particularly unsettling is that the machine learning models don't always agree with the traditional physics-based models about which stars are most likely to explode soon. There are stars that the AI flags as high risk that physicists would say are probably stable for another 10,000 years, and vice versa. This could mean the AI is picking up spurious correlations, seeing patterns in noise. Or it could mean the AI is detecting subtle signals that our physics-based models are missing, precursor signatures of instability that we haven't learned to recognize yet. We won't know which interpretation is correct until some of those stars actually explode, and we can compare predictions to outcomes. Betelgeuse, in this context, might not be special at all. It might just be uncomfortably close. If we were observing it from 10,000 light years away instead of 650, it would be a faint, unremarkable red supergiant in a catalog of thousands, probably not getting much attention unless it happened to dim dramatically during a survey observation. But because it's close, because it's bright, because it's in one of the most recognizable constellations in the sky, we watch it obsessively. We've built entire observing campaigns around monitoring its variability. We've deployed interferometers to image its surface directly. We've measured its mass loss, its rotation, its spectrum, its polarization, and all that attention has revealed a star that's far more complex and unstable than we expected. The broader implication is that if Betelgeuse is typical rather than exceptional, then we need to reconsider our understanding of how massive stars end their lives. We need better models that include rotation, binary interaction, asymmetric mass loss, and time-dependent envelope structure. We need more observations of other red supergiants to see if the patterns we're seeing in Betelgeuse generalize to the wider population. And we need to be prepared for the possibility that when Betelgeuse finally does explode, it might not behave the way our textbooks say it should. It might be asymmetric. It might launch jets. It might produce a light curve that doesn't match any of our existing templates. And if that happens, we'll have to throw out a lot of assumptions and start over. The most humbling part of all this is realizing how much we still don't know. Stellar evolution is one of the most mature fields in astrophysics. We've been studying stars for over a century. We've built sophisticated models that can predict main sequence lifetimes, track nuclear burning stages, calculate supernova energetics. And yet here we are, looking at a star 650 light-years away, watching it do things we can't fully explain, and admitting that our best answer to the question, when will it explode, is essentially a cosmic shrug. Maybe soon. Maybe not. We'll find out when it happens. And in the meantime, we're discovering that Betelgeuse isn't alone, that there are other stars out there equally confused about how they're supposed to die. The universe is messier than we thought, and mess is much harder to predict than order. There's a shift happening in astrophysics that most people haven't noticed yet, a quiet reorientation of perspective that has profound implications for how we think about the relationship between the sky and the ground. For most of the 20th century, astrophysics and geophysics were separate disciplines. Astrophysicists studied stars, galaxies, black holes, things happening out there, far away, disconnected from daily life. Geophysicists studied Earth, its interior, its atmosphere, its magnetic field, things happening down here, immediate and tangible. But over the past few decades, those boundaries have been eroding. We're starting to realize that what happens out there doesn't stay out there. The cosmos reaches into planetary systems in ways we're only beginning to measure. Space weather is the most obvious example. We've known for over a century that the sun affects Earth through solar wind and coronal mass ejections that disturb our magnetosphere, creating auroras and occasionally disrupting power grids and satellite communications. That's direct, measurable coupling between a star and a planet. But the sun is just one star, and it's relatively quiet compared to some of its more violent cousins. What happens when you scale up the input? What happens when, instead of a gentle solar breeze, you get a supernova shockwave delivering a sudden pulse of high-energy radiation and particles? We don't have a lot of data on that, because supernovae close enough to affect Earth directly are rare on human timescales. But they're not rare on geological timescales. Recent work from 2025 has been digging into the geological record, looking for signatures of past supernova events, and what they're finding is intriguing. There are layers in deep sea sediments and ice cores that contain elevated levels of certain isotopes, iron-60, for instance, that don't occur naturally on Earth, but do get produced in supernova explosions. The isotope ratios suggest these deposits came from a nearby supernova a few million years ago, close enough that Earth would have been bathed in a significantly elevated cosmic ray flux for thousands of years. And during roughly the same time period, there's evidence of increased cloud cover, slight cooling in global temperatures, and possibly some changes in atmospheric chemistry. Correlation isn't causation, but it's suggestive. The mechanism is complex, but the basic idea is straightforward. High-energy cosmic rays entering Earth's atmosphere ionize molecules in the upper atmosphere, creating charged particles that can act as condensation nuclei for cloud formation. More cosmic rays, more ionization, more cloud nuclei, potentially more clouds. More clouds mean higher albedo, which means Earth reflects more sunlight back into space, which means cooling. It's a subtle effect, not enough to trigger an ice age by itself, but enough to nudge climate in a measurable direction if it persists for long enough. And if a nearby supernova increases cosmic ray flux by even a modest factor, sustained over millennia, those nudges could add up. The Betelgeuse supernova, if and when it happens, won't be close enough to deposit significant amounts of radioactive isotopes on Earth. 650 light-years is too far for that. But it will increase cosmic ray flux measurably, at least temporarily, and we'll be able to study the atmospheric response in real time using instruments that didn't exist a few decades ago. We have satellite networks monitoring radiation levels, atmospheric composition, ozone concentrations, cloud properties, and a dozen other parameters continuously. When Betelgeuse goes supernova, it'll be the first time in recorded history that we can observe the coupling between a stellar explosion and a planetary atmosphere with modern scientific instruments. That's an unprecedented opportunity, and scientists are quietly planning for it. The planning involves coordination between astrophysicists, atmospheric scientists, and space agencies to ensure that when the supernova happens, we're ready. There are proposals to increase monitoring frequency for certain satellites, to deploy additional instruments to measure specific atmospheric effects, to establish baseline datasets now so we have something to compare against when the event occurs. There's also discussion about public communication strategy, because when Betelgeuse explodes, it's going to be spectacular and visible to everyone, and there will be questions. People will want to know if they're safe, if their children are safe, if this is dangerous. And the answer will be no. It's not dangerous, but it is significant, and we need to be clear about what that means. The intersection of astrophysics and planetary science is producing some fascinating insights that go beyond just supernova effects. Researchers are using stellar observations to inform climate models, recognizing that stars, especially young, active stars, can drive significant atmospheric evolution on their planets. We're learning that planetary magnetic fields interact with stellar wind in complex ways that can protect or erode atmospheres over millions of years. We're discovering that cosmic ray flux varies on galactic scales as the solar system orbits through different regions of the Milky Way, and that variation might leave imprints in Earth's geological and biological record. There's also the AI-driven stellar modeling angle, which is starting to produce results that surprise even the researchers running the simulations. Machine learning algorithms trained on vast datasets of stellar observations are finding correlations between stellar properties and supernova behavior that traditional models missed. Some of these correlations don't make intuitive sense yet. The AI is saying stars with these specific combinations of rotation, mass loss rate, and surface temperature are more likely to produce asymmetric explosions. But it's not always clear why. Figuring out the physical mechanisms behind those correlations is an active area of research, and it's forcing astrophysicists to reconsider assumptions about how rotation and mass loss couple to core collapse. One of the more speculative but intriguing possibilities that's emerged from this work is the idea that we might be systematically underestimating how often astronomical events affect planetary environments. Not in dramatic, extinction-level ways, but in subtle, cumulative ways that add noise to climate systems, influence long-term habitability, and occasionally trigger shifts that get attributed to other causes. Earth's climate is driven primarily by solar input, orbital variations, and internal feedbacks like greenhouse gas concentrations and ocean circulation. But there's a growing recognition that external forcings from cosmic sources, supernovae, gamma-ray bursts, variations in cosmic ray flux, even the passage of the solar system through dense molecular clouds, might contribute more to climate variability than we've been accounting for. This isn't suggesting that cosmic events cause all climate change, or even most of it. It's suggesting that the climate system is more porous to external influences than we tend to acknowledge, and that over geological timescales, those influences might matter in ways we're only starting to quantify. Betelgeuse won't cause climate change when it explodes, but it will provide a data point, a single, well-observed example of how a moderately close supernova affects a planetary atmosphere, and that data point will help us calibrate models for events that happened in the past and might happen in the future. The final question to leave hanging, the one that ties all of this together, is whether we're underestimating how often the sky reaches into Earth's systems. We tend to think of the cosmos as distant and disconnected, a beautiful backdrop to our terrestrial concerns, but not something that directly affects daily life. And for the most part, that's true. Stars are far away. Supernovae are rare. The universe mostly leaves us alone. But occasionally, rarely, the universe reminds us that we're not isolated. We're embedded in a galaxy full of energetic, violent phenomena, and some of those phenomena are close enough to touch us in ways both subtle and profound. Betelgeuse is a reminder. It's a star we can see with our naked eyes, a familiar beacon in the winter sky, and it's on the edge of exploding in an event that will briefly make it one of the brightest objects visible from Earth. We don't know when. We don't know exactly how it will look. We don't know what the full range of atmospheric effects will be. But we know it's coming, and when it does, it will be a moment that connects astrophysics and planetary science in a way that hasn't happened in recorded history. We'll watch a star die 650 light-years away, and we'll feel it here, in our atmosphere, in our magnetosphere, in the subtle shifts of radiation and particles that link the fate of stars to the fate of worlds. And maybe, just maybe, after watching Betelgeuse explode, we'll start asking more seriously, what else is out there that we haven't been paying attention to? What other stars are quietly approaching the end of their lives? What other energetic events are unfolding in corners of the galaxy we don't monitor closely? How many times has the sky reached down and touched Earth without us noticing? Because we weren't looking for it. The universe is vast, and most of it is silent and dark, but every now and then, something bright and violent happens close enough to matter. Betelgeuse is our warning, our preview, our chance to prepare. And the countdown, whether we like it or not, has already begun.